Hello, everybody. Today is our third lecture in this week. It's about chapter 2, in which we'll speak about convective mass transfer, and we are dealing with mass transfer coefficient. But this lecture is very interesting and enjoyable. Why it is enjoyable? Because we'll be dealing with two objectives. First is we are going to define dimensionless groups of mass transfer, which are corresponding to those for heat transfer. I'm not sure if so far you got some dimensionless numbers or groups for heat transfer, but if not, I will still cover them. And also then I want to convert the correlations of data on heat transfer to correlation on mass transfer. We spoke earlier in the first chapter regarding history. We said that heat transfer was understood and experiments were conducted for heat transfer much earlier than mass transfer. So in that case, should we repeat everything for for mass transfer, or should we use the data which are available for heat transfer into mass transfer? Well, the answer, as you can guess, is that it is better to make a kind of intelligent way so that we can get all information from heat into mass. Now, the first thing is we are going to lay the ground and we have defined our dimensionless groups. So, most practically useful mass transfer situation involve turbulent flow, and for these, it is generally not possible to compute mass transfer coefficients from theoretical considerations. We used uh, laminar flow to uh, get some of the correlations. However, when it becomes more turbulent, becomes more complicated and it is difficult to do some theoretical foundation for that. So in that case, we must rely principally on experimental data. So rather than trying to find uh, variables using basic theoretical, it is better and easier to do experimental data for turbulent flow to get information. So there are many more experimental data available for heat transfer than for mass transfer. And we agreed on this because we said historically the heat transfer was much earlier and lots of people have done lots of experiments. We'll take one example very soon. So to convert equations or correlation of data on heat transfer to correlation on mass transfer, we are going to use dimensionless groups of heat transfer and we'll replace them by corresponding group of mass transfer. So this is what we will do. We will replace the heat transfer dimensionless group with mass transfer dimensionless groups. So that will be our aim. So what are these dimensionless groups? This table shows you a kind of summary for both of them. You can see heat transfer and mass transfer. The first one, dimensionless group, which is very familiar, you are with, the Reynolds number. Reynolds number for the heat and mass transfer are the same. So Reynolds equal rho ud over viscosity. And instead of d, we are putting L, which means the characteristics length. So for a tube, for example, you are going to use the diameter. However, something else, you have to use also the shape of that pipe, etc. So rho ud over viscosity, let's agree on that. Then you have the, for heat transfer, Prandtl number. Prandtl number, specific heat multiplied viscosity divided by the K. K is the thermal conductivity. The corresponding dimensionless group for Prandtl number is, we call it Schmidt number. Schmidt number for mass transfer. So we can replace Prandtl with Schmidt. So what is the Schmidt number? It is again depending on physical properties. It is viscosity, is density, and it is the diffusion coefficient, diffusivity, DAB. The third dimensionless group is called Nusselt number. Nusselt number is equal to H, convective heat transfer coefficient, multiplied by characteristics length, divided by the conductivity or heat conduction. So it is a ratio of H divided by K multiplied by the L. So that's your Nusselt number. Since we are dealing with convective, so we are going to use the mass transfer coefficient. So the corresponding dimensionless number is Sherwood number. Sherwood number is defined, as you can see, is few equations, but all of them have what we call it mass transfer coefficient. And mass transfer coefficient from the previous two lectures, we said it can be F, it can be Kg, it can be Kc, it can be Kc prime, it can be Ky prime, depends on the situation. And we already had two lectures speaking about unimolecular diffusion and equimolar counter diffusion. So based on that, we have few definitions for the mass transfer coefficient. You have also some other numbers like Grashof number. Grashof numbers for the heat, GRH, is equal to G gravitational force multiplied by some other parameters like L, rho, beta, which is volume coefficient of expansion, multiplied by delta T divided by viscosity squared. And you can also have a Grashof number for mass transfer. There are other numbers like Piclet number. Piclet number is relating Reynolds and Prandtl number, and it is also can be defined for heat transfer as CPL V rho divided by K. And Piclet number for the mass transfer, it is also Reynolds number multiplied by the Schmidt number. Now, this is very interesting. So what happened for Piclet number for heat and mass transfer? If you look, the Reynolds stays the same because at the beginning we said the Reynolds number for heat transfer and mass transfer, they are the same. Correct? Look, RE didn't change. But for the Prandtl number, which is for heat, has been replaced by the Schmidt number. The Prandtl number just directly replaced by the Schmidt number. So you can see how easy it was to move from one form to another form. Again, you can also do same thing for a Stanton number. Stanton number for heat is defined as Nusselt divided by Reynolds divided by Prandtl. You can now replace the Nusselt by Sherwood number. Reynolds will stay as it is. Prandtl number will be replaced by Schmidt number. So if a Stanton number is equal for the heat equal Nusselt divided by Piclet, you can just replace the Piclet from heat to Piclet by diffusion, which is mass transfer. There is another form also, it's called Chilton-Colborn J factor. This is, we'll deal with it in another separate lecture, but you can see JH is equal to Stanton number for heat multiplied by Prandtl number to the power 2 over 3. Now look, the Chilton-Colborn for the mass transfer, so instead of JH, it becomes JD, and Stanton for heat becomes Stanton for diffusion, which is mass transfer. And another thing, the Prandtl number will be replaced with the Schmidt number. And Schmidt number, the power stays the same. It didn't change. So 2 to the power 3 stays 2 to the power 3 there. So you can now try to understand what's happening. So using dimensionless group, we managed to change from heat transfer to mass transfer. So this is our target. So the next few slides are basically defining to you what is the meaning for each one of these dimensionless group. So Schmidt number is dimensionless number defined as the ratio of momentum diffusivity, or we call it kinematic viscosity, and mass diffusivity. So if we go back, Schmidt number, it is viscosity divided by rho divided by diffusivity or diffusion coefficient. So that's the thing. And it is used to characterize the fluid flow in which there are simultaneous momentum and mass transfer convection processes, since we have both of them together, the momentum, which was the ratio of the viscosity and rho, and you have also mass diffusivity, which was the mass diffusion coefficient. And the person who did it is called Schmidt, and he is German. The Schmidt number is the ratio, again, of the diffusivity, viscosity divided by density to the diffusivity for mass transfer, which is capital D. And it relates physically the relative thickness of hydrodynamic layer and mass transfer boundary layer. Mass transfer boundary layer was dictated by the diffusivity or diffusion coefficient, whereas the thickness of hydrodynamic layer is the ratio of the viscosity and density. So Sherwood is equal to viscosity divided by density divided by diffusion coefficient. The other number was Prandtl number. I did it in red. That means it's related with the heat transfer. So it is analogy for the Schmidt number, and it is dimensionless number. Also is being devised by German. His name is Prandtl, and it is basically defined as ratio of momentum diffusivity to thermal diffusivity. So the definition of Prandtl number is given to you, and at the end you can see the ratio of the momentum diffusivity to the thermal diffusivity. And you get the final form of it, which is Cp viscosity divided by K. Another important number was the Sherwood number. Sherwood number is English, so it is the dimensionless number used in mass transfer operation, and it represents the ratio of convective mass transfer to the rate of diffusive mass transport. So Sherwood is equal to KCl divided by D, which is convective mass transfer rate divided by the diffusion rate. The diffusivity or diffusion rate is capital D, and convective was the mass transfer coefficient, so Kc multiplied by L. The heat transfer, it is the Nusselt number. Nusselt number is basically the ratio of the convective heat transfer divided by conductive heat transfer. So the convective is H divided by KL, so the ratio will be HL divided by K. So that's the meaning of Nusselt number. So now what we'll do, this is the last part of the lecture in which we are going to apply these. This example is divided into few parts. So you should try to understand the first part, the question itself, then we'll start solving for the physical properties. The physical properties can be given to you, or it can be given to you in the exams, or you have to find them. But it is a bit lengthy process. So let's read the question. For a flow of fluid at right angle to circular cylinder, so you have a circular cylinder and there is fluid flowing past it. The average heat transfer coefficient averaged around the periphery of the cylinder is given by equation developed by Eckert and Drag. So these two, they have done heat transfer relationship, and they found this correlation. The correlation is basically Nusselt number as a function of Reynolds number as a function of Prandtl number, and this is valid for Reynolds number between 1 to 4,000. So you can see the range of Reynolds number, it is linear, and then you have the Prandtl and Reynolds number to give you the Nusselt. So Nusselt average and Reynolds are computed using the cylinder diameter as the characteristic length, and the fluid properties are evaluated at average conditions, because at the end of the day you have the density, viscosity, but all of these are depending on the temperature. So which temperature you will be using? This is the average condition. So this is what you are supposed to try to find. So estimate what he wants you to find. Estimate the rate of sublimation of a cylinder of UF6. So it's a kind of uranium fluoride, and it is molecular weight 352, quite heavy. The diameter of this cylinder is 1 centimeter, and the length of this cylinder is 10 centimeter, and it is exposed to air stream that flows normal to the cylinder axis at a velocity of 1 meter per second. So you know the materials now, the material of the cylinder and the fluid around of it is air. The surface temperature of the solid is 303 Kelvin, at which at that temperature the vapor pressure of the uranium is 27 kilopascal, which you can get it from the handbook of Perry and Chilton, and the bulk air is at 1 atmosphere and 325 Kelvin. So it is a bit hotter than the temperature of the cylinder. Viscosity of the mixture is given to you. So this is the kind of diagram showing you what is happening. So you have the cylinder, which is made from solid UF6. On the surface, the temperature is 303 Kelvin. The vapor pressure of that solid material is 27 kilopascal. When it comes to the at the end of the stagnant gas film in which there is air, the partial pressure of the UF6 is basically zero. It is because there is too much air compared to the UF6. Velocity of the air and the pressure, total pressure is given also to you. The direction of the flux is from 1 to 2. So you are supposed to find the rate of transfer of UF6. So first step is that you will replace the Nusselt with Sherwood. So the same equation, we just replace the Nusselt with Sherwood. Reynolds stays at the same, and the Prandtl will be replaced by Schmidt number. So now you get the equation, which is Sherwood as a function of Reynolds and Schmidt. The power stays the same, and the range of the Reynolds number stays the same. Now, we did the first step. We are supposed now to do some other things. Other things, that means we have to find some physical properties, the diffusion coefficient, etc. But you have first to sort out the temperature. So along the mass transfer path, the point 1 and point 2, the average temperature is 303 plus 325 divided by 2, so that will be the average temperature, 340 Kelvin. And at point 1, the UF6 we said is given to us, which was 27 kilopascal. So in that case, you can find the mole fraction. Mole fraction for the average condition is 27 plus 0 divided by 2. So it is 13.5 kilopascal, your pressure. And if you want to change it to mole fraction, So then you take the 13.5, you divide it by total pressure, which is 1 atmosphere or 101.3 kilopascal. Then in that case, the mole fraction of UF6 is 0.133 at average condition. Using ideal gas law, you can estimate now the average density of the gas film. Before that, you have to find the average molecular weight. Average molecular weight was UF6 and the air. So in that case, 13.3% is UF6 and the rest is air. So 352 multiplied by 0.13 plus 29 multiplied by the remaining mole fraction of the air, which is 1 minus 0.13, and you will get 72 as the average molecular weight. After you get the average molecular weight, now you can find the density at average condition. Since it is gas, you can say it is Pm over RT. The M will be average molecular weight and T will be the average temperature. The R is constant and the total pressure is constant. So in that case, you get the density around 2.8 kilogram per meter cube. You know that the air density is around 1.2 kilogram per meter cube, but since you have something heavy like UF6, then 2.8 seems reasonable. Now, this is a kind of methodology to find the viscosity. You are not supposed to do it in the exam because it is quite long process. However, it is worth to have a look and understand it. This method is called method of locus and it is valid for the non-polar gases. So what we want to find the viscosity. So viscosity R multiplied by M is equal to the xi, it's called xi M, multiplied by the viscosity is equal to function of reduced temperature. So now we have to find most of these values so that you can apply this equation. It looks weird a bit, but we'll go and find each one of them. So this xi in the equation, xi m here, it is defined as follows. It's 0.176 multiplied by few parameters. What are these? It is the critical temperature of the mixture, TCM. PCM is critical pressure of the mixture. And you have also TRM, which is temperature divided by the critical temperature. So that's what each one of them means. Another thing is in the previous equation, there was F at the end. You can see FTRM. Basically, you can find it as a function of reduced temperature of the mixture. So if you have the reduced temperature of the mixture, you can find this value FTRM. And the critical temperature of the mixture is basically the mole fraction multiplied by the critical temperature of that component. PCM, you can get it from this equation, which is RTCM multiplied by YI multiplied by Z. This Z, if you remember from thermodynamics, it was basically the compressibility factor. And the molecular weight is basically the mole fraction multiply molecular weight for each component. So this is a kind of table explaining to you what's happening. So you have the air. Air is basically oxygen and nitrogen. 21% is oxygen, and the rest is 79% nitrogen, and the rest is UF6. So if we want to find the mole fraction, Yi, 21% of 0.867, the rest was 0.133 was UF6, and the 79% of the 0.867 was nitrogen. Critical temperature of oxygen, nitrogen, and UF6 is given to you possibly from tables. Critical temperature is given to you, molecular weight is given to you, VC critical volume is given to you, and the compressibility factor is given to you. So now, if you have all of these parameters, you can substitute and find the values. So for example, if you want to find the critical temperature of the mixture, then you have to use this equation, the first equation, in which you have mole fraction multiplied by the critical temperature of each component. So if you did that for this table, then the critical temperature of the mixture is around 181.9 Kelvin. You can do similar thing, find critical pressure of the mixture, applying this equation, which is including compressibility factor and the VI. If you do that, it will be 40.3. And then also you can find the reduced temperature of the mixture. If you find the reduced temperature of the mixture, then you can find also other parameters. Now you can find the Xi. Xi basically we said it is a function of critical temperature, average molecular weight, critical pressure of the mixture. So since you have all of them, now you can find the Xi. Another thing, you can find also this F function. You can find it, and it is around 0.962. If you find this Xi and the F function, then you can go back to this equation, the previous equation, which is the method of locus, and you can find the viscosity. So you have all of them now, except the viscosity. You can find the viscosity. It will be around 229 micropoise, or it will be 2.29 10 to the power minus 5 kilogram per meter per second, and this is the SI unit. This is what you want. Now, why we did all of that is to find the Reynolds number. Reynolds number, you know, definition, rho UD over viscosity. So now you have the density of the mixture. We calculated was 2.8 kilogram per meter cube. Viscosity we calculated, it is 2.29 10 to the power minus 5. And then you have the characteristic length, and which was, I think it was 1 centimeter, was it? And the velocity 1 meter per second. So if you find it, you can find now Reynolds number is around 1223, which is basically less than, or it is in the original range, which was up to 4,000 for the Reynolds number. After you find that, your assignment were asking you to find diffusivity or diffusion coefficient, and which you use a kind of software. Now this diffusion coefficient from the first chapter, you can use now this kind of a routine, MathCAD routine, or whichever routine you use, and to find the diffusion coefficient. Now I'm going to assume that you already have done this, and you can calculate it, and it's around 0.0904 centimeters square per second. Now you find the diffusivity. Now you can find the Schmidt number. We define the Schmidt number. Let's go back and see what is the definition of Schmidt number. So Schmidt number, it is basically viscosity divided by density divided by diffusion coefficient. Now we have viscosity, density, and diffusion coefficient. So let me go back. Now you apply it, it will be Schmidt number 0.905. And then now you can substitute in the mass transfer coefficient correlation, in which there is Sherwood as a function of Schmidt and Reynolds number. So Sherwood now is equal to 18.4. Remember that Sherwood was relating to mass transfer coefficient. However, you have to decide which type of mass transfer coefficient is needed for these two components when they are moving from one place to another. So is it unimolecular diffusion or it is equimolar counter diffusion? So that's the question. It is basically a case of unimolecular diffusion because the air was not transferring from the outside to the solid surface. So in that case, NB was equal to 0. So in that case, we have this stagnant gas film. So in that case, this is our case. So that means what? That means we have to use one of the forms of the unimolecular diffusion. But unimolecular diffusion depends also on concentration. So it was it dilute or was it concentrated? Since the mole fraction given to you was 13.3%, that means you are supposed to use F type of the mass transfer coefficient rather than the K type. So in that case, you are supposed to use the equation for Sherwood, which include the F-type mass transfer coefficient. So if you go back to the previous set of equation, then Sherwood is equal to FD over CDAB, and that's equal to 18.4. So if you know all of the others, you can know now the F-type mass transfer coefficient. You can calculate concentration since it is gas, so you can assume it is ideal gas law, so P over RT, and the T, it should be average temperature because it is in that film. So you got the C, you got the DAB, you got the small d. So in that case, you can find the mass transfer coefficients. If you got the mass transfer coefficient, and since there is the bulk term in it, and you are using the unimolecular diffusion, so you can use now the flux. Flux is equal to Fg multiplied by the length term. So that means the bulk term is there. So 1 minus YA2 over 1 minus YA1. And A was for the UF6. So now you can calculate the flux. Flux will be 2.02 and the power minus 4 kilomole per meter square per second. Now, you have it as kilomole per meter square per second. We want to change it. We want to make it kilogram per second. So that means you have to get rid of the area and change also the kilomole to kilogram. That means the molecular weight. So since you have uh, the cylinder as a shape, so for the cylinder, total surface area will be the surface of the whole of the cylinder. That means uh, two basically circles up and down and the pi dl. So pi d square over 4 plus pi dl plus pi d square over 4. So then you get the total surface area. So you can get out of the meter square. Then now you have to find also the molecular weight, but molecular weight is of the UF6 only. It's not the average or whatever, because you are dealing only with the unimolecular diffusion. It is only the UF6. So now you can find how much kilogram per second is there, which is diffusing from that solid cylinder to the air. So that's that. So basically, this lecture was about defining dimensionless groups. So now you know that there are different dimensionless groups for heat transfer and for mass transfer. And also we managed to convert a kind of correlation of data of heat transfer to correlation on mass transfer. So without going and doing experiments for mass transfer, we use the old relationship for heat transfer, what some people have done it experimentally and change it to mass transfer. So have a good day.